Okay, welcome back everybody to Python for Physics. We are on our last week, week 8. If you're new to the course, today we're going to take a little departure. This is a course that introduces concepts of programming using Python as a tool to solve physics problems. Today, as I said, we're going to take a little departure. So instead of talking about programming, we're going to have a little introduction to quantum mechanics. Quantum mechanics is one of the building blocks of modern day physics, and Dr. Fatma Aslan is going to give us a little introduction. I've introduced her in the past, so you're familiar with her. She's a postdoc here at Jefferson Lab and also University of Connecticut, but she's physically here at the lab. So thank you so much, Fatma, for taking your time to giving us an introduction to quantum mechanics. So take it away.
Okay, thank you. So I'm sharing my screen, right?
Yep.
Okay, so I'll give a little introduction to quantum mechanics. Hopefully you don't need a background to understand. I put out of pictures, tables, and a few videos. Hopefully it will be easier to understand. Now, before the modern physics, the only known description of nature was classical mechanics. That is before 1900s. And it works it can explain the behavior of the objects which are macroscopic in size and that are also slow. And that was the only scale the scientists could observe back then. Slow and big, everyday world. But as the technology improved, they could make experiments in a faster speeds, like comparable to the speed of light, and also microscopic scales, like the size of an atom. And that they saw that classical mechanics fails to explain the both directions. It cannot explain the behavior of the objects that move comparable to the speed of light. Now there is relativistic mechanics today can do that, or size of the atomic sizes. Again, it fails to explain those that scale. Today, quantum mechanics can do that. So when we say the relativistic mechanics, for example, for comparable to speed of light, it's not only for high speeds. The relativistic mechanics covers all the speed spectra. Similarly, quantum mechanics is not only for atomic size, it's for all the sizes. But still we use classical mechanics because it's not practical to use quantum mechanics in bigger sizes or relativistic mechanics in slow speeds. And quantum field theory is the combination of relativistic mechanics and quantum mechanics for the objects that are very small atomic size and they move comparable to the speed of light. That's, for example, the particles, elementary particles. That's why we use quantum field theory in particle physics. And also one remark, there is two types of relativistic mechanics. There is special relativity and there is general relativity. Special relativity is only for inertial reference frames. There is no acceleration, no speeding up, slowing down, or changing direction. The generalization of the special relativity is general relativity that works for non-inertial frames too. But only special relativity combines with quantum mechanics to make up the quantum field theory. And general relativity is usually out of those pictures. So we said that classical mechanics fails to explain atomic sizes. And what does it mean to fail to explain? It means that it cannot tell what's going to happen. It makes a prediction, but the reality is different. That doesn't happen. For example, classically an electron, atomic electron, spirals down and collapses into its nucleus because it radiates energy as it collapses, as it moves, accelerates. But we know that atoms do not collapse and they make up the visible matter in the universe. So that's a failure. It predicts that atoms cannot be stable, but observation is around us. Also, another example is it cannot explain the spectrum of black body radiation. Black body means an object that absorbs all the light falls onto it. So a hot object, a hot such object, the electrons in that object vibrate. And as a result, the light is emitted. So the heat is actually the kinetic energy of the vibration, and light is due to the acceleration from the vibration. The hotter the object gets, they vibrate more, the electrons vibrate more, they emit more light, and there is no limit to this, classically. So the graph on the side, it shows UV catastrophe. That's classical prediction. As the frequency increases, which means low wavelengths, there is no limit to the energy. It can go to infinity. Classic prediction. But what we see in nature is actually there's a peak and then it goes down. So it cannot explain this situation in classical physics. Another one is photoelectric effect. Photoelectric effect is you shine a light on a metal and the electrons come out. Classically, light is an electromagnetic wave and the energy is distributed along this wave. For the electron in the metal, on the metal surface, to absorb the energy from the light takes time, and it again needs time to build up the energy to escape from the surface. And there's a time delay. Classical physics says it takes time for the electron on the metal surface to build up enough energy to escape the surface. But observationally, there is no time delay. You shine a light and the electrons come out. So the details are not important, but what important is classical mechanics make a prediction, but the reality is different. So that's what failure is. It cannot tell what's going to happen, or it tells something and it's wrong in reality. That happens as well as in special relativity too, but we are going in the quantum direction. Now, why does it fail? We say classical physics fails in the microscopic world, and why so? Because classical physics approaches the nature as pure particles or pure waves. For example, you throw a rock in the water and waves form. In classical physics, okay, they both carry energy and momentum from one place to another, but they are separate disciplines. They are separate concepts. For example, there is acoustics for sound waves, optics for light waves, mechanics of particles. They have different disciplines. But when we go to microscopic world, there is no such distinction in the sense that we know waves and particles. There's no waves and particles. There is a wave-particle duality. For example, we say electrons are particles because they have localized charge and mass, but it's also correct to interpret a moving electron as a wave. For example, we say light is an electromagnetic wave because it shows interference, diffraction patterns, and polarization. But it's also correct to say in some situations, the light is made up of stream of particles called photons. So there is waves and particles, separate concepts in classical physics. Whereas in quantum physics, there is no distinction. There is not particles and waves, but there is particle-wave duality. And that's the central difference and why classical physics fails. Now we say, okay, a particle is associated with a wave. We can say a particle behaves like a wave, but these are called matter waves. But what are those waves actually? Because we say that there has to be, in order to call something a wave, there has to be a quantity which diverges from the equilibrium. For example, we have sound waves. As the wave goes through the medium, the particles oscillate around back and forth, around the equilibrium position. So in this case, what changes is pressure. For example, another example is water waves. As the wave goes through the water, the particles make circular motion, and what changes is the surface height of the water. Or there is electromagnetic waves, like what changes here is the amplitude of electromagnetic and electric and magnetic fields. Reds are the electric and blue shows the magnetic field, and they oscillate perpendicular to the propagation of the light. So what is this? What oscillates or what changes in the case of matter waves? It is called the wave function, which is a function of space and time. And its value at a particular space, at a particular place at a time, is proportional to the probability, likelihood to find the body there. So it's actually the probability of its presence. So it's a probability of presence. Now the wave function itself, it's not directly the physical, it doesn't have a direct physical interpretation, because when we say probability, it's between 0 and 1. So say 0 means the object is not there, definitely. 1 means the object is definitely there, and it can be some value in between. Say 0.3 means there's a 30% of chance that you find the object there. So the wave function itself can be negative, therefore, but the probability has to be positive, so therefore we use the square of its absolute value, which is called probability density.
Fatma, sorry to interrupt. I think some of us are having a hard time hearing you right now.
I'm sorry, maybe I should get closer. How is it better?
It sounds a little fuzzy. You don't have a mic?
No.
Okay.
I'm getting closer. Does it make a difference?
It sounds a little better.
I'm talking.
Yeah.
It makes a difference? Okay, I'll talk like this. It's ugly, but oh well.
This is what I had to do.
Okay.
Do you recall? Yeah.
Okay.
Yeah.
So okay, there's a misconception. I should have mentioned this before. One thing comes into the mind is like this wave function. Thinking about what is that wave function? Is it like the particle is spread along, so its charge or mass is spread? Is that wave? But it's a big misconception, because we use this for elementary particles. Like there's no such thing as 20% of an electron. Or we make an experiment, we find the electron there, or we don't find it there. There's no such thing like we find 10% of the electron somewhere and the rest is somewhere else. So this is a misconception. Wave function, it's the probability of the whole presence. If the probability density is big, the chances you find it at some point are big. If it's small, the chances you find it there is small. But as long as it's not 0, there's always a chance that body is at a certain point. Now here is an overall picture again. Now there was classical mechanics, but it failed to explain the atomic size. It predicts something, but it doesn't happen, because there is waves and particles, separate things, separate concepts in classical mechanics. Whereas in quantum mechanics, there is no waves and particles, there is the wave-particle duality. A particle is associated with a wave. And what type of wave is that? It's probability of its presence. Now, what is central is the wave function in quantum mechanics. And how do we get that wave function? Through Schrödinger equation. Since we are talking about quantum mechanics, not quantum field theory, if you know some physics, there is Dirac-Popper equation or Klein-Gordon, but we are talking about quantum mechanics, so it's just Schrödinger equation to get the wave function. Now, a good analogy is to make an analogy. A good explanation is to make an analogy with classical mechanics. For example, in classical mechanics, say a particle, an object of mass is under the influence of a force. A force is applied. The task is to find the position of the mass. Once we know the position, we know everything. We know the acceleration, velocity, kinetic energy, momentum, any physical quantity. And how do we do that? We use Newton's second law. Along with Newton's second law, if we know the initial conditions, we can tell where the object is going to be at a future time. That's the position. For example, a very simple example that's very common in introductory physics class. Say we have a mass, everything is one-dimensional, so we don't have to worry about changing directions, vectors, one-dimensional. There is a force, like we talked about, applied to an object, to a mass. We know the initial conditions, the initial velocity, and the initial position, say it's 0. And the question is where it is going to be 10 seconds later. So classical mechanics, by applying Newton's laws, can tell you that. For example, we just apply F is equal to ma, Newton's second law. We know the force, we know the mass, and we know if we find the acceleration, our task is to find the position. Since it's the second differential of the position, we solve that differential equation, which you learned about 2 weeks ago in this class also. By solving this differential equation, if you know the initial conditions again, you can tell it's going to be at that position 10 seconds later. So that's classical mechanics. Okay. In quantum mechanics, now the central thing is to find the wave function instead of the position of the particle. And how do we do that? By applying the Schrödinger equation, just like Newton's second law. We apply the Schrödinger equation if we know and we need to know the initial wave function, then we get the wave function, just like we apply the Newton's second law and we get the position. But there is something different, which is, C is the probability. In classical mechanics, we apply the force, we know the initial conditions, we can tell what's going to happen in the future. What's the position, and from there we can tell what the other quantities are. Whereas in quantum mechanics, we apply the Schrödinger equation and we get the wave function, which just tells us the probability of finding a particle. It still tells the future, but it cannot say it with a certainty. There is only a statistical information. So that's why classical mechanics, we say, is deterministic. We know exactly what's going to happen in the future. Whereas quantum mechanics, probabilistic. We just know statistical information. Now, this was disturbing to scientists because as well as it can be a fact of nature, it can also be a defect in the quantum mechanics. So they asked this question. Suppose we measure the position of the particle and we find it to be at a certain point C. Where was the particle just before we made the measurement? Now, 2 views stood out against this question. One is realist view, also advocated by Einstein. He said the particle was at C, yet the quantum mechanics was not able to tell us because there are some hidden variables. There are some properties that we don't know in quantum mechanics. The quantum mechanics doesn't know. That's why it cannot tell where the particle is going to be exactly. But once we improve the theory, then it's going to be like classical mechanics, deterministic, not probabilistic anymore. So it's a defect in the theory, which are also called hidden variables. But there was another view, Copenhagen view, and one of the famous advocates was Bohr. And they according to this view, they say the particle was not really anywhere. The act of measurement put it into a place. So who was right? I put a video. It answers this question also through double slit experiment. It explains the wave particle duality a little bit. Now we look at this video. How do I go? Okay.
So, what they taught us in school isn't really the way it is, and that our senses are playing tricks on us. You just gotta wonder, what is this reality that we find ourselves in? Quantum physics says it's all just waves of information. Do I believe that? I hope so. Yikes! And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. Physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of 2 bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. It was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
Okay. So which view was correct? It was Einstein was wrong. The realistic view was wrong. There is no hidden variables. What is the correct view is the Copenhagen view. The measurement puts the particle in a definite state. So there are 2 distinct kinds of physical processes here. One is the ordinary ones, in which the wave function evolves under the Schrödinger equation. So it's a wave. Then a measurement is made and the wave function collapses suddenly, discontinuously. And so how did Copenhagen view was proven to be the right one, not the realist view? Like there are no hidden variables. Quantum theory would explain everything better if we knew more about the particle state. This is explained by Epr Paradox, which actually came from Einstein, Podolsky, and Rosen. They were trying to prove that their view, realist view, was the correct one, and the Copenhagen view was the wrong one. But they ended up proving the other way around, through Bell. Well, in this case, they considered the decay of a pion. The pion decays into an electron and a positron. And they are, according to the conservation laws, everything doesn't matter, the details. One particle is in spin up and the other is in spin down position. So again, it doesn't matter what spin is or up or down. There is a quantity related to each particle. One, for say electron, is going to be up, say a vector, and the other has to be down, or the other way around. The electron is going to be down, then the positron is going to be up. So they're always going to be opposite of each other. Now, they thought, okay, the pion decays and electron and positron, they fly opposite way from each other. It can be 10 meters, it can be 10 light years or 100 light years. Once, by the way, the quantum mechanics tells, it doesn't tell which one is which, but it tells, remember, the probabilities. Quantum mechanics tells 50% of the electron, 50% of the time, the electron will be spin up and the positron will be spin down. 50% of the time, it's going to be the other way around. The electron is going to be down and the positron is going to be up. Now, when they fly apart from each other, say 100 light years, it's far so that they cannot communicate to each other. They make a measurement on the, say, electron, and they find it to be spin up. So immediately we know that the other one is spin down. Now this, according to Einstein, proves realist view, because there's nothing interesting with this outcome, because the electron was already spin up. And all we need to do is to make the measurement to learn about this. And once we know one is spin up, we know the other is going to be automatically spin down. It's like Einstein's analogy is like you separate two gloves, a pair of gloves, you put one glow in one box and the other in the other box. And then once you open one box, if you find the left pair, you're gonna know that the other one is right. It's not like it was undetermined from the beginning. Now they put their idea on the basis of special relativity, because they say if it's not in the if in a definite position, it has, for example, electron is spin up, it has to tell the positron to be spin down. But in this case, when they are 100 light years apart, it cannot be immediate because it has to, the information has to travel. So the Copenhagen view cannot be right. But that's a paradox. So there's a twist to their question. And Bell proved that the Copenhagen view is correct. Now again, I'm going to show a video about Epr paradox and how Bell proved the Copenhagen view is correct. They don't have a particular state until the measurement. The measurement puts them in a definite state. So how do they communicate? Or is it even a correct question to say communicate? Okay, this next is the video. Then I have one more slide left on Bell's theorem. Okay, this is a longer one.
Two of the biggest intellectual giants of modern physics changed our view of reality and proposed their theories around the same time in the early 20th century. Yet their views about reality were completely different. Niels Bohr, one of the founders of modern quantum mechanics and the father of the Copenhagen interpretation, argued that reality, or the state of a particle at the fundamental level, was not only unknown, but was unknowable until it was measured. Albert Einstein passionately disagreed with this idea and believed that reality was knowable and that probabilities could not completely define reality, that there had to be an objective reality out there independent of measurement. He famously said in his dramatic statement, "Do you really believe the moon only exists when you look at it?" Bohr and Einstein argued passionately about their views on the essence of reality, and for 30 years both views were considered equally valid, and scientists chose sides. Then in 1964, Irish physicist John Bell devised a way to prove whether Einstein's view of a classical deterministic view of reality was correct. And he put this in a simple, elegant equation called the Bell inequality. Although the equation is simple, understanding what it means is not so easy. So how did this simple equation disprove the ideas of the most famous and powerful scientists of the 20th century and forced us to confront the unsettling truth that we may live in a fundamentally non-deterministic universe? The answer is coming up right now.
I'm sorry. I wanted to skip some ads that he makes, but I think I'm gonna have to start it. Oops. Oh, he talks about his channel, so I want to skip that part.
Hey, Patman, just so you know, it's starting to get a little muffled for me too. Again, so.
My voice?
Yeah, your voice.
Oh, I'm sorry. I missed it again.
It's okay. The video sounds perfect. It's just
Yeah,
it's just yeah, it's just your mic.
Okay, I'll get closer. I have one left on me.
No, you're fine. You're fine. Just I think maybe just be careful that you're not blocking any mics with your hand or something.
Okay. Let me see. Okay, that's his ads. Okay, that's the ads. Okay.
I'm delighted to tell you that Magellan TV has an exclusive offer right now for Arvin Ash viewers. If you use the link in the description, you'll get 1 free month trial. I highly recommend Magellan TV, but be sure to use the link in the description. The central weirdness of quantum mechanics can be demonstrated with the toss of the dice. If the dice was a quantum system like a photon, electron, or atom, it would be in superposition. That is, its position and other properties, in a sense, would be up in the air, like a dice thrown before it hits the table. It's a 1, 2, 3, 4, 5, and 6 all at the same time. According to the most accepted interpretation of quantum mechanics, the Copenhagen interpretation, pioneered by Niels Bohr and Werner Heisenberg, it's not only that the dice's value is not known, but that it is all values at once. Its value can only be known once it is measured. The double slit experiment demonstrates this. A single photon passing through the slit should not be thought of as a particle going through and interacting with itself. Rather, it's like a three-dimensional wave or a cloud of probability when it is emitted. This wave can go through both slits at once and interfere with itself like a wave does before it is measured by the photosensitive screen in the back when it resolves to a specific location on the screen. Einstein, who was the most famous scientist at the time, was bothered by this interpretation of quantum mechanics. The idea that part of nature remains not only unknown, but is unknowable unless measured. That's why he famously said, God does not play dice. So Einstein, along with two other scientists, Boris Podolsky and Nathan Rosen, EPR for short, came up with what they thought disproved the Copenhagen interpretation. The crux of their argument rested on the idea of a phenomenon predicted in quantum mechanics called entanglement. Let's say we have a quantum system that has zero angular momentum, also known as spin zero, and it emits two photons simultaneously. Since photons have spin and since angular momentum must be conserved, if one photon has a spin up, the other photon must have a spin down. So the spin up and down cancel each other out. This is entanglement. The two photons are not independent. If the spin of one of them is known, the spin of the other becomes known instantaneously. Now let's separate these photons far apart. Let's say 300,000 kilometers, which is about 1 light second away. Now, according to quantum mechanics, each of these photons is governed by a wave function, and each photon is in a state of both spin up and down at the same time. It is not up or down, it is both up and down. However, the wave function of these photons is not independent. They're really the same wave function governing both photons. Now, if we measure the spin of one of them, we have a 50% chance of detecting a spin up. Let's say we do detect spin up. Now let's measure the spin of the other photon in less than 1 second. It should also have a 50% chance of having spin up or spin down, but it doesn't. It has a 100% chance of having a spin down. This means that the information of the collapse of the wave function of one of the photons had to travel faster than light to affect the other photon. EPR argued that since nothing can travel faster than light according to the rules of special relativity, this should invalidate the Copenhagen interpretation. This theorized violation is the EPR paradox. EPR proposed instead that there is likely another theory which would show that the two entangled photons were in cahoots from the very beginning, that their states were predetermined from their creation. In other words, their states contained the information locally so that when they were moved apart, no communication had to take place. The information that we were measuring was hidden inside the two particles. This is called local hidden variables. So for example, it's as if the two particles were a pair of gloves. One was a left-handed pair and the other was a right-handed pair. Once we found the left-handed pair, we knew immediately that the other pair, no matter where it was in the universe, must be a right-handed pair. This was a valid interpretation of quantum mechanics for almost 30 years. From 1935 to 1964, this could not be disproven. This is where Irish physicist John Bell comes in. And in 1964, he proposed an experiment that could show whether the local hidden variable theory was correct or incorrect. Now, Bell's equation is remarkably simple, but it's one of the most difficult to understand and simplify. So I'll present a highly simplified idea of how it works, then also show you the simplified version of the mathematical underpinnings later in this video. Now we're going to play a game, and our opponent is going to be the universe. And the game is guess the color of the checkers pieces. Now I want to give a big shout out to Jim Al-Khalili, who shows a similar simplified illustration in a documentary available on Magellan TV. I encourage you to check it out because it's fascinating. If I guess the color correctly, I win. If I'm incorrect, the universe wins. In the first game, I declare that if the colors match, I win. The universe picks the pieces. Now in play after play, I find that I lose every time. So in the next round, I change the rules. This time I declare that if the colors are different, I win. The universe picks the pieces. In play after play, I find that I lose every time again. So I conclude that perhaps the universe has rigged the game against me. This is what Einstein suspected was happening, that the checkers pieces were rigged. He believed that the colors of the pieces were predetermined, and that this information had been known from the very beginning when the two pieces were together. Niels Bohr's idea, on the other hand, was that the red and black don't even exist until the piece is turned over. So I changed the rules of the game again. This time, I do not tell the universe whether matching colors or different colors will win the game until after the universe has already picked the checker pieces. If, after revealing the checker pieces, I find that I win 50% of the time and lose 50% of the time, then my conclusion is that indeed the checker pieces were rigged from the very beginning, because my chances of winning would be 50% if the red and black pieces were already picked by the universe. But if I continue to lose, then I have to conclude that somehow the colors of the checker pieces were not chosen ahead of time. Let's look at how Bell's elegant equation proves my conclusion. To do this, let's look at a universe where local hidden variables are correct. In other words, entangled particles have predetermined properties which are complementary to each other at the moment of their creation. Note that this is not an interpretation of quantum mechanics, it's an alternative to quantum mechanics. So in this system, when two entangled particles are produced from a process that conserves linear and angular momentum, we will get two particles that go off in opposite directions, and they will have opposite spins as well as opposite directions. Let's say Alice makes the measurement on particle 1 in her laboratory, and Bob makes the measurement on particle 2 in his laboratory. And let's say the two labs are very far apart and are not in communication with each other. If Alice measures the particle spin in the z direction as positive, Bob will measure the spin as negative in the z direction. If they measure the spin in the x direction, which is orthogonal to the z direction, or 90 degrees apart, the same type of complementary opposite spins will be measured. Because as I said earlier, angular momentum is always conserved. What Bell's inequality does is it says, now let's make a third measurement that is somewhere in between the z and x axes. In our example, we use 45-degree angles to the z and x direction. We'll call this the q direction. So in a universe where local hidden variables are true, when the two particles are emitted, they know what their state is going to be in all three directions, z, x, and q from birth. And there are only 8 combinations or possibilities of spins that each particle could have. So for Alice and Bob, these 8 combinations will be the following. The event 1 could be where the spin in the z direction is positive, the spin in the x direction is positive, and the spin in the q direction is positive. E2 is when z is positive, x is positive, and q is negative. E3 is when z is positive, x is negative, and q is positive. E4 is when z is positive, x is negative, and q is negative. E5 is when z is negative, x is positive, and q is positive. E6, z is negative, x is positive, q is negative. E7, z is negative, x is negative, and q is positive. E8, z is negative, x is negative, and q is negative. Now let's ask the question, what is the probability that Alice measures in the z direction, gets a positive spin, and Bob measures in the x direction and gets a positive spin? Well, if the above case is for Alice, there are 4 events where z is positive. In order for Bob to get x positive, Alice would have to have measured x as negative. So these would be in events 3 and 4. To get the probability, we have to divide by the total number of events, which is 8. Let's do this for 2 more scenarios. What is the probability that Alice measures positive in the z direction and Bob measures positive in the q direction? In this scenario, it would be event 2 and 4. Again, we divide by 8 to get the probability. And the third case is, what is the probability that Alice measures positive in the q direction and Bob measures positive in the x direction? This would be event 3 and 7, divided by 8 for probability. So these are the 3 probabilities given the hidden variables theory. Now, here's the big insight that John Bell had. If I take the total number of events and multiply that by the probability that Alice measures Z positive and Bob measures X positive, this has to be less than or equal to the total number of events times the probability that Alice measures Z positive and Bob measures Q positive, plus the probability that Alice measures Q positive and Bob measures X positive. When we write this out, the 8 cancels out and we are left with just the probabilities. This is Bell's inequality. Now I can prove this is true by doing simple math. E3 plus E4 divided by 8 is equal to E2 plus E4 plus E3 plus E7 divided by 8. The 8's cancel out and we rearrange the order of addition and we're left with this. E3 plus E4 is less than or equal to E3 plus E4 plus E2 plus E7. This makes total sense because E3 and E4 are on both sides of the equation, and E2 and E7 have to be positive. So this inequality absolutely has to be true for any hidden variables theory to be true. Now remember, these probabilities are for a universe with hidden variables. But what happens in a universe where the laws of quantum mechanics are correct and not the hidden variables theory? Well, this inequality is violated in quantum mechanics. How is it violated? Let's say Alice measures the spin to be positive in the Z direction. Then we know that if Bob measured the particle in the Z direction, he would get a spin that is negative. However, Bob doesn't measure in the Z direction, but in the Q direction. What will the spin of this particle be? In hidden variables, there was a 50% chance that it would be positive and a 50% chance that it was negative. But this is not what happens in quantum mechanics because the measurement of the particle follows the probability laws of the wave function for a particle rotated 45 degrees. And that probability of Bob measuring Q to be positive after Alice has measured Z to be positive, if the angle between them is 45 degrees, is given by the following equation. Sine squared of 45 degrees divided by 2. This comes from the math of quantum mechanics. This is the critical difference between quantum mechanics and hidden variables theory. The probability that Bob measures the same spin as Alice, depending on the difference in angle measured, is not linear, but looks like a sine wave. When you plot this out, this is what the probabilities look like. You can see from this graph that at 0 and multiples of 90 degrees, the two systems are in agreement. But in between, like at 45 degrees, the probability is 25% for hidden variables and about 14.6% for quantum mechanics. But the proof is in the pudding because in test after test, the sine function correlation has been confirmed. The particle does not behave linearly, and so the hidden variables theory cannot be correct. Bell's inequality is violated. So we can write out and compare Bell's inequality for both cases. For hidden variables, the equation would be E3 plus E4 is less than or equal to E3 plus E4 plus E2 plus E7. 2 is less than or equal to 4. The inequality holds true. For quantum mechanics, the equation would be sine squared of 90 degrees divided by 2 is less than or equal to the sine squared of 45 degrees divided by 2 plus the sine squared of 45 degrees divided by 2. And when you solve this, you get 0.5 is less than or equal to 0.293, which of course is not true. So Bell's inequality is violated in quantum mechanics, which is exactly what we observe in experiment after experiment. Now, does this prove that the two entangled particles are communicating faster than light? There is differing opinion on this. On the surface, it does appear that superluminal communications is taking place, but my personal opinion is that no communication is happening. The two particles are really just part of one wave function. And since the wave function can theoretically be as wide as the universe, when this one wave function collapses, both particles collapse. And since the collapse is random, it cannot be used to communicate in this way. So most theorists do not think special relativity is violated because we can't communicate using this seemingly faster than light phenomenon. But our knowledge of quantum mechanics and entanglement is incomplete to say the least. Why is there superposition? What is the mechanism of wave collapse between two particles separated by space and time? I happen to think that the scientist who's going to reveal the mystery of quantum mechanics is alive right now in the world. And I can't wait for him or her to explain this. And like Copernicus, Newton, and Einstein, completely change our paradigm. I'll see you in the next video, my friend.
Okay. Now he explains the Bell's theorem, but more about its significance. So it proves that Copenhagen view is correct. There are no hidden variables like Einstein thought. So probability is in the nature of quantum mechanics. It's not missing any hidden variables. And one of the textbook explanation is to the entanglement. So there's one thing that there's wave function, and measurement puts it in a definite state, which is not known before. And there's, on top of that, there's entanglement, like how do the electron and positron in the EPR products communicate. So that's another point. And one explanation to this is actually the speed of light is not the limit. It's limit for causality to send information or receive information. So scientists talk about two types of influence. That one is causal, but it can be also ethereal too. So causal influence is, it cannot propagate faster than light because it delivers or receives information from the other particle and it makes actual changes. So in EPR paradox, it says they cannot communicate, but if they don't communicate, they are not violating the special relativity. Another influence would be that there is no constraint on the speed of the propagation. But the thing is, it doesn't transmit energy or information. And we just know that it is an influence because there's a correlation in the data. For example, what can that be? Faster than light. For example, there's an example here, but another example I know is easier to understand. For example, you shine a flashlight on Jupiter. So it's so far and you can shine the whole diameter. And if you shoot a bullet through in front of your flashlight, the shadow of the bullet is going to pass the diameter of the Jupiter faster than light. But it's just a shadow. It can't do anything. You cannot. It cannot affect anything. So that would be a ethereal type of influence. And the answer, one of the answers to the paradox, is the wave function collapse is not causal, but it's ethereal. So there's no problem in the EPR. And if you buy it. That's all I want to say. Now, my references, I prepared this, most of the context, the pictures are mainly from Wikipedia. Two books I used is Introduction to Quantum Mechanics by Griffith. So I took the analogy of classical and quantum mechanics from that book. Also, explanation of EPR Paradox Bell's equality. I strongly recommend this book. And the other books is Concepts of Modern Physics by Arthur Beiser. And I also added the links where I took the pictures, videos from, if you want to look at them, watch them again. So that's all I want to say. Thank you.
Great. Thanks, Fatma. That was a lot of fun.
Yeah.
Let's see if anybody has any questions. I don't see any right now. I see there's a lot of people in the call, but I don't see anybody asking questions. What's that?
It means I can
Well,
explain better. Okay, I'm stopping.
yeah, well, let's just wait a second because there's a little bit of time delay. So maybe they do have questions in a second. To the TAs, does anybody see any questions, or do they have any questions of their own? Maybe I'll comment that the history of quantum mechanics to me is is so fascinating, and the role that Einstein played is really amazing to me. The fact that he was originally one of the founders of quantum mechanics, right? Introducing the photoelectric effect, which led the foundation to everything that resulted, that went forward. And same thing for Max Planck. But then at the end, later on in his history, he was such a anti-proponent, right? He was so it was just an interesting character that he liked to be seen as a rebel rouser early on, but he struggled with being a stubborn person later on in his life. So yeah,
it's fun to say Einstein was wrong, right? Like
yeah,
he was wrong.
Yeah, it's good to know that he wasn't perfect in everything. So
yeah, I felt the same. Like Warren was better.
Yeah,
it's very difficult, that idea anyway, right? Like what he advocates is not that deep, but the other one is way more of imagination.
Yeah, I mean, he would call it, what was it? He would call it something like spooky effect or something like that.
Spooky action at a distance.
Spooky action at a distance. That's right. Yeah, I mean, it is strange, right? And his views and his perception of how the universe works, for a great deal of physics turns out to be quite right. Just quantum mechanics is a sticking thumb into this beautiful image of what the universe should look like. So it makes sense that he would struggle with that. So. Well, I don't see any comments or questions at this point. So, and maybe to everybody out there, if if quantum mechanics doesn't quite make sense to you, or these ideas seem a little I don't know, too weird to be true, that's okay. You're in good company. I think everybody struggles understanding quantum mechanics at first, and even when you've thought about it for some time, it's always strange. And the important thing is that it's driven by experiments like testing, like Bell's experiment. So it's something that we see over and over again that does describe experimental data quite well, remarkably well. And it's the predictions that we've seen come from quantum mechanics and later on quantum field theory are the most precise that we, the most accurate predictions that we see in science. So it is true, but it takes some time to digest. So.
Well, I think thinking about wave function is like thinking about a fourth space dimension. We can do it mathematically, but it's okay if we cannot imagine it. Like I always see it that way. It feels more comfortable. Like we can say, like, okay, fourth dimension, you'll be able to see inside of a three-dimensional object. You can say or do all the math, but you cannot imagine it. Wave function is like that to me, a little bit. I mean, the position one at least.
Right. Yeah. So Oh, go ahead.
Fatma, you got a question. Actually, shall I go? Hello?
Yes, it says I'm listening.
It's Brian from Medan, Indonesia. And Brian says, hi, Fatma. Thank you for the presentation of quantum mechanics. There are some questions I have been wondering the answer. The first one, what is the difference between quantum mechanics and quantum field theory besides the Gordon equation, which is Schrödinger equation and Dirac or Klein-Gordon equation? That's the first question.
Schrödinger. Okay.
Well,
Schrödinger.
You want?
Schrödinger equation is quantum mechanics, and when we go to quantum field theory, it's spin 0 is Klein-Gordon, spin 1/2 is Dirac, and spin 1 is Proctor equation. So that's the difference. The Schrödinger equation is not used in the quantum field theory. Any more comments? Like more to say?
Maybe the question is trying to ask what is the difference conceptually between quantum field theory and quantum mechanics? What were the problems that were seen in quantum mechanics that were needed to be, that led us to introduce quantum field theory as a framework for describing, as you said, small objects that are moving at high, that are moving really fast?
Yeah, I'm thinking about like antiparticles are in quantum field theory, or like a lot of new concepts getting when we think about quantum field theory. One is spin is not definitely just relativistic, but in quantum mechanics we put it by hand. But in quantum field theory, it's embedded in the equations already. And one of the advantage and the difference is antiparticles coming also in quantum field theory. And yes, like it's also for relativistic.
Right. So I think that's a really important that's a really important example, right? That you can within the quantum field theoretical framework, you can quite easily describe the production of new particles as well as the antiparticle annihilations. And so I think that's a good motivation for using quantum field theory. It becomes more natural in that framework rather than in quantum mechanics.
Mm-hmm.
It's maybe worth pointing out that Schrödinger actually tried the Klein-Gordon equation first before taking the non-relativistic limit. Like if you try to make a wave function out of something relativistic like the Klein-Gordon equation, at least in the mid-20s, when the way they were trying to do that, you get weird things like negative probabilities that don't make any sense. You manage to avoid by taking the non-relativistic limit first.
Juan, did you want to read the second part of the questions? Yes.
The second one is a bit long, so I will try to go very slowly. The second question that Brian has is the following. What problem did physicists start to think about QFT? And why it is named as QFT and not quantum relativistic theory? In other words, how do the field work come out?
So I think the question is, why do we use fields to describe particles, right? Do you want to try to explain that, Fatma?
I would say why we need to use fields, and then that's a natural question why the name is quantum field theory, I would say, instead of quantum relativistic theory. Yeah. So
I was on and off hearing, but I'll so we can say, I think, quantum relativistic, right? But when we say field, we also deal with many particles. That's true. It's only not one particle theory. It's many body particles, many body theory. True. That's why it is also called field. Because whenever we are actually formulating the quantum field theory, we talk about degrees of freedom as particles, and then we take that number of modes to infinity. So it's not only for one body, also it's for field, many particles. Any more comments? I cannot hear, or nobody's talking.
Can you hear me, Fatma?
Okay. I think it's on and off. I think. Okay. It's
Okay.
fine. I can fill in the blanks.
Sounds good. Maybe I can read the other question. So see, we have Luis Ángel Vergara Ortiz from Mexico saying, okay, in what could someone work by? Okay, I think maybe Luis Ángel, do you want to maybe try to rewrite the question? I'm not sure I understand it completely. But the second half, I think basically they're asking is, what can you gain from studying quantum mechanics? Like, why do we need quantum mechanics, and what new knowledge do we gain from it? Can others that have access, other TAs that have access to the questions, can you try to interpret it and see if my interpretation makes sense?
The interpretation that I got of the question was, what jobs could you do using quantum mechanics?
I think you're right. Okay, yeah. What kind of jobs could one get? Yeah,
you can work on quantum Volkswagens and quantum BMWs, right?
yeah.
Okay. For example, there was in one slide I talked about photoelectric effect, right? So solar devices use that. I mean, that type of jobs you can get, because like you need quantum field, not quantum, the quantum mechanics, like photoelectric effect, for example. You cannot explain it with classical physics, which is also used in solar devices, solar energy.
I mean, I think one example that is really topical and related to what you were talking about is quantum information science.
Oh, true. Yes, quantum computers, right?
Yeah. So quantum computation, quantum information science. There's a lot of interest. There's a lot of investment. In fact, in the U.S., that is a field that is rapidly growing, where the government has invested quite a bit of money to go into quantum information science, which uses this idea of entanglement between particles to communicate information that is perhaps encrypted and that is safe for, that can travel large distances, so you can communicate with people across the world and be able to keep that information secure. There's also interest in using new classes of computers that are not classical, but rather that use quantum information, that use quantum techniques to be able to do different classes of computations that are not readily accessible with using classical computers. So those are two fields of science that are rapidly growing, that use the basics of quantum mechanics at their foundation, I would say.
Mm-hmm. Mm-hmm.
Okay, let's see what other questions we have. So we have a question. Okay, so we have a question that is a little long. Let me see if I can make sense of it. Rahul Silva. Oh, that sounds very close to Rahul from Colombo, Sri Lanka. Hello, Sri Lanka. Saying, hey, I was wondering if there is a theory for universal hidden variables, if there's a theory of local hidden variables, or am I just restating the wave equation? So let me try to read it again to see if it makes sense. Can you hear me, Fatma?
Mm-hmm.
Okay. So the question states, I was wondering if there's a theory for universal hidden variables. I think there's a comma after that. If there's a theory of local hidden variables, or am I just restating the wave equation?
My understanding is like, is there any type of other hidden variables? Like, does it have to be only local hidden variables? Do I get it right? Or some?
I think so. Maybe you can explain why the idea was to have local, why locality was important in this hidden variable theory. Maybe that's the source of the confusion. I'm not sure.
locality it comes from special relativity, because we know that there is a limit to causality, which is the speed of light. Then again, if you're not carrying information from one point to another, if it's not causal, it doesn't have to be, I guess. It doesn't contradict with special relativity. So local is just means it obeys, it doesn't contradict with special relativity. And non-local would be the other way that we talk, like it's faster than light, but it's not causal. It won't it won't send information. So maybe that would be called non-local, the ethereal, what they textbooks call. Or, yeah, right, local.
Yeah.
And
Yeah.
what can it be non-local, which doesn't obey special relativity, goes faster than light? Yeah, that's what textbooks call ethereal, I guess. Ethereal, yeah. But in that case, it's not causing. It's not, because it's not causal. I would say, if it's an answer.
Well, let's see. Rahul, maybe you can tell us if that's a satisfying answer. So we have another. What's that? Well, or maybe he can or they can rephrase the question if it's not, if this was not the answer that we're looking for. We have another question from Zhou Leo Chao from Taiwan, saying, so first they apologize for not having a direct question, but then they have other questions, so no need to apologize. I guess they're saying that they're not even close to the level of physics yet, but I am curious, what do you think of a high schooler can do if I want to pursue this path? Is coding important? And they have another question, but we can maybe tackle the first one first. Do you have any recommendation for high schoolers, or perhaps you can tell us about your path, what got you from high school to where you are at, and which things you think worked, and perhaps what are the things you wish you would have done different that perhaps you can recommend to others?
Well, coding, I'm not really using, but I'm sure it opens you more doors. You guys do coding, so you would know better than me. I'm just calculating things by hand. And like, I would recommend read as much as you can, but don't try to understand everything perfectly, I would say. And because like, okay, I can give the classical advices, but one thing I would think that is not a classical advice would be get used to feeling stupid. This feeling will never go away. Like sometimes I read things, and if I understand it at once, I'm like, that's something wrong. I cannot understand things reading at once. So just like, I would say don't give up, because that increases your chances, like quantum physics. And don't have pride about this. Like, I don't understand, so I should give up. Like people who make it that far, they usually don't have that type of feelings, because people who has that, like, oh, I feel stupid, like I won't be able to answer that question, that's a constant feeling you have to deal with. So either you don't care about these things, or you won't be able to get that far. So I would say don't get discouraged because things are difficult. Just enjoy the ride, I would say. You won't get, even though you don't get anywhere, just watch, read, and whatever, I would say enjoy the ride.
Yeah, that's great advice. I think
you guys can talk about maybe coding, because I don't know, and that's very popular. People ask about it all the time.
Yeah, I mean, so although I program now, I didn't learn how to code until grad school. So I took a coding class when I was an undergrad, but I didn't really take it that seriously. So I think all of you that are in in this class with us and learning how to code, you're far more advanced than I was at your age. So I think you're doing far and beyond a lot more than most people would do. So you're doing a great job. And I think to Fatma's point, like, I think not being discouraged and not, I think this idea of getting comfortable with being stupid, I think is a good one. I think when I was a younger age, I would feel more sometimes I think I absorb information better when I think of it as like, if I don't understand something, I'm more if I have an attitude of being curious about it and wanting to learn about it, I'm much more productive rather than when I feel like, oh, I should know this. Why don't I know this already? Right? I think it's okay to feel comfortable with not knowing and in fact enjoying that feeling. So and so Leo said to ignore the second question, but he did have a nice comment at the end. He said, "Thanks again for this wonderful talk. It was really interesting." So,
thank you.
Yeah, and I agree. It was a really nice talk. So thanks so much, Fatma.
Thank you.
I think we don't have any more questions at this point. So
I was expecting more questions about quantum physics, not quantum field theory, because there's a lot of mysterious about quantum entanglement or wave function. Yeah. Okay.
Yeah. Well, I think maybe that wraps it up for today. So, on Thursday is going to be our last class. We're gonna introduce some new topics and do some new exercises that you're welcome to do on your free time. As I've mentioned before, all the videos and materials are going to be left indefinitely online for you to use. So you're welcome to use them whenever you're ready. And we're going to keep the Slack chat open so we can continue having conversations with you as you progress. And also you can talk to each other about the challenges that you face. And also, if you want to start doing a project related to using the tools that you've learned during the class, you can continue running those projects, not during this next week, but continue running them indefinitely into the future. So we highly encourage you to do that so you can keep practicing on your skills and keep developing tools that we believe are going to be useful for your research career and your academic career. So with that, thank you so much again, Fatma, for taking your time and preparing such a nice talk and giving it and sharing it with us. So thank you. And thanks to everybody. And we'll see you again Thursday.